Hello and welcome back. So far we have understood the complete process of building a data science module or executing a data science project, like splitting data, then taking train set only, and then doing EDA, feature engineering, then passing it to the model, testing it on train set, looking at the accuracy, if needed, fine tuning the model. Then when the model is working good on train set, testing it on test set and see whether the overfitting problem is there or not. On our multiple linear regression dataset, the salary prediction dataset, when we built a model, we have seen only 62% accuracy. That means the model is underfitted. And we have understood theoretically that when the model is underfitted, we may have to improve the model's accuracy by making the model more complex. For linear regression, if you want to make the model more complex, we need to apply polynomial regression, or we should add the polynomial terms to the dataset. When you add polynomial terms to the dataset and pass it to the linear regression, it becomes polynomial regression. We have seen that in the intuition of the polynomial regression class with a small example. Okay, so let us try to do the polynomial regression on this dataset and see what happens. So what we are trying to do is, we took a dataset and did whatever we can using linear regression and found something, and we are now trying to improve the model's accuracy. This is what we have to do in real time also. So let us jump in and do whatever is needed. So I have imported all the necessary modules here: pandas, numpy, matplotlib, and cbar. And linear regression shuffle split, shuffle split is to split the data, random splitting the data. I have downloaded the data into the data frame, and then I am looking at the head, which is actually showing the first five records. And now I am splitting the data into train test. The data got split into train and test, and it's a random split, shuffle split. And we have got 1209 records in the train set and 303 records in the test set. Now we need to do data pre-processing. We know what pre-processing should be done on this data set, because when we built multiple linear regression, we have done some preliminary analysis and did some kind of quality check, and replaced the lines of code negative values with 0, right? And then we have imputed the nulls in the years of study with mode, and qualification also we imputed with mode, and then the degree, the degree also imputed with mode, right? All the columns we imputed, all the null values got imputed with mode values. And employee number is not of any use. It's a categorical column, but it has got distinct values for each record. So we removed that also. It's not going to be, it will not have any predictive power to predict the salary. So we removed that as well, right? Then we were actually trying to convert the categorical columns to numbers. We used label encoding. To do that, we actually converted each categorical column into a categorical data type. To do that, we need to pass the allowed values of each column. So to do that, we have created a dictionary of allowed values for each column. Designation, all the allowed values; qualification, all the allowed values; degree, all the allowed values, like that. And then in a loop, right, when you call this method by passing your train set and all the categorical columns, right, in a loop, we are trying to invoke or take the corresponding allowed values and passing them as categories, so that the categorical data type will assign appropriate numbers to each category, right? When you say the column is equal to column.cat.codes, it will automatically assign the values. It will actually, for senior developer it may have assigned 0, for analyst it may have assigned 1, for senior analyst it may be 2, like that, right? Wherever it finds senior developer, it will assign 0. Wherever it finds analyst, it will assign 1. Like that, in the dataset it will convert. So that when you execute this code, this particular code, right, the total data becomes numerical, because all categorical variables we have converted to numbers. Now I am splitting the data into XY, train X and train Y. We are working on train set only, because until and unless the model works good, we are not going to touch the test set. Okay, so the train set, train X and train Y, all the columns except salary we have taken into the X. and salary we have taken into y. So now we have the data ready, right? Now we can build a polynomial regression model. How will you build a polynomial regression model? Using polynomial features, the class, we will actually pass our train set and fit transform. To do second degree polynomial, we have to pass the polynomial features and degree is equal to 2. What it will do? It will create n plus d by n plus d factorial by n factorial into d factorial number of columns. What are those columns? x1, x1 square, x2, x2 square, x1, x2, x2 square, sorry, x1, x2 square, x2, x1 square. Like that it will create all the polynomial terms, all the interaction terms and polynomial terms. So when we have like around 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, around 12 columns I think it has got, right? 12 or 11. 11 columns are there. So it's going to create 11 plus d is 2. 13 factorial divided by 11 factorial into 2 factorial. Now it's going to be 13 into 12 by 2, right? So it's going to create 78 columns. Okay, if we said bias term is equal to 1, so it's going to create 78 columns. So it created 12,009 rows and 78 columns. So we have polynomial terms added to the dataset. The X-train poly dataset has got polynomial terms. When you pass X-train poly dataset to the linear regression, it becomes polynomial regression. Okay. So let me execute the statement so that it creates the polynomial terms. Now I am passing the data to the linear regression algorithm and saying fit. When I say fit, it's going to form all those polynomial equations is equal to y, and then solve all of them at once and then find the thetas. Now we have got thetas here. So if you use the model to predict, the predictions will come, right? The predicted values will come. So the predicted values are there. Now we can actually calculate R square score and root mean squared error. So I imported the metrics, the R square score, R2 score and mean squared error. Now I am calculating R square score. To calculate R square score, you need to pass the original observed y values and the predicted y values. The difference square is going to be RSS. The original value, the observed value minus mean of it and square is the total sum of squares. Using total sum of squares and residual sum of squares, it's going to calculate R square score. R square score should be close to 1 to say the model is working good. And mean squared error, the observed value minus predicted value whole square, sum of it and mean of it, divided by m. Okay, the squared sum of all the residuals divided by total number of records, 1209 records, is going to be mean squared error. When I apply square root to it, it's going to become root mean squared error. So let us look at how much accuracy we have got. It's actually 90% accuracy. On a linear regression model, we have got only 62% accuracy. Here, after making the model polynomial regression, on the train set, we have got 90% accuracy. This is a good news, right? The model performance improved. We were able to successfully improve the model's performance by increasing the complexity on the model. But let's wait. We may have encountered or entered into a overfitting problem. What is overfitting problem? When model works good on train set and not works good on test set, it's a overfitting problem, right? So when overfitting problem happens, if you make the model too complex, then it is required. And let us check that. When the model is working good, we can actually touch the test set and test it. On test set also, we need to apply all the data transformations we have done on train set, because in the test set so far we haven't touched the test set. So there are there may be lines of code negative values, there may be some null values in the years of study, qualification, degree, educational institution, and there are categorical columns definitely, right, which we need to convert into numbers, and we need to convert into numbers with the same numbers it assigned to the train set, so that the model performance will not change. Okay, so let me execute this statement. So we have converted all the test set into the same shape as the train set, and now I am splitting the test set into x and y. Right, now I need to apply the polynomial features here. So see this, if you observe this here, I did only transform, no fit. Why? Because on the train set we have done the fit. That means we understood the data, or we actually understood how many degrees it should create. Right? On test set here also, when you are doing transformations on test set, we have taken all the understandings from train set only. Years of study impute value, qualification impute value, degree impute value, all these values we have got from the train set only. I have explained this before, right? The train set will have more number of records. When you take inferences from the train set, they are going to be more appropriate in terms of total data. The sample size is big. The understanding is going to be better. So that understanding we need to apply to the test set or production. So we are doing the same thing. So even for the polynomial features also, you shouldn't do fit on the test set. You should do only transform. So I transformed. So I've got 78 features here. See, we need to get 78 features, 78 columns only on the test set also, because when you actually passed your train set, the number of features you passed is 78, right, to the linear regression algorithm. The equation is going to have 78 terms, theta 0 plus theta 1 x1 plus and so on, theta 78 x something, like some n, right, 78 or something like that, right? So if the equation is having 78 terms, whenever you pass data, it should have 78 terms only. When you do this kind of, you take the, all the understanding from train set and use the transformations or all the pre-processing steps what we have applied on the train set, if you apply all those only, you will get 78 columns in the same shape. So we have done that. Now the test set is eligible to pass into the predict method. I passed it, I predicted. I have got 91% accuracy. That means the model is working good on train set and test set both. That means we have found a best model here. But we don't know whether this is the best model, because we built a linear regression. We built a second degree polynomial regression. I don't know whether maybe third degree polynomial is better or fourth degree polynomial is better. Right? This is called as model selection. In the coming session, right, we will understand resampling techniques and the model selection approaches. Thank you.